और कोई भी आ रहा है या शुड वी स्टार्ट?
I think so. They might be joining. We can wait for one or 2 minutes more.
Okay, sure. Okay, so I
Sir,
think yes,
yes, sir.
we
Everyone
can
has
start.
joined.
Yeah, thanks. Okay, let me share my screen.
सर एक्सक्यूज मी।
हाँ, बोलो।
सर ये वाली का जो पेपर आपने दिया था उसका सबमिशन का लास्ट डेट क्या है?
आई थिंक अब जल्दी ही सबमिट कर दो। आई थिंक टाइम तो हो गया है काफी। कितना टाइम हो गया? 1-2 हफ्ते तो हो गए शायद।
हाँ सर 10 दिन हो गए उसके।
हाँ, एक्चुअली ये तुम लोग प्रेजेंटेशन कब देने वाले हो?
सर प्रेजेंटेशन आप बताइए सर, जितना जल्दी हो सके दे देंगे।
क्योंकि तुम्हारा एग्जाम वैसे 26 से होगा शायद।
हाँ सर 26 को सर हमारा पेपर है।
तो मतलब एग्जाम टाइम में देना है या उससे पहले वाली लास्ट क्लास में भी दे सकते हैं? मतलब क्या करना है, कैसा करना है, वैसा सोच सकते हो। आई थिंक हाफ एन आवर प्रेजेंटेशन विल बी एनफ फॉर बोथ ऑफ। अच्छा, इंडिविजुअल प्रेजेंटेशन देने वाले हो तुम लोग या अलग अलग?
सर इंडिविजुअल अलग
मतलब
अलग मतलब?
मतलब सॉरी, इंडिविजुअल देने वाले हो या फिर कंबाइंड?
सर आपने इंडिविजुअल कहा था लास्ट टाइम सर।
हाँ ठीक है, इंडिविजुअल का था। ठीक है। हाँ, मैं सोच रहा था, सॉरी, मैं सोच रहा था ग्रुप 2 बने हुए। ठीक है। हाँ, अलग अलग मेरे को, हाँ, ईमेल आ गया था। ठीक है। तो कब करना चाहते हो तुम लोग? 26 के टाइम पे करोगे या उससे पहले करना है? हम लोग लास्ट क्लास में भी कर सकते हैं, वट एवर यू वांट।
सर लास्ट क्लास मतलब मई में जो क्लास होगा उसकी बात कर रहे हैं आप?
नहीं, आई थिंक अभी हम लोग की आखिरी क्लास कब है बेसिकली? आई थिंक नेक्स्ट वीक है शायद ना, एग्जाम से पहले।
हाँ राइट एग्जाम हमारा 26 से स्टार्ट हो जाएगा, तो उसके पहले ही अगर लास्ट क्लास है सर।
तो अगर तब तक तुम लोग रेडी कर लेते हो तो तब भी कर सकते हैं, या फिर उसके बाद तुमको करना है, मतलब यू नो मतलब 26 वाले वीक में करना है तो तब भी कर सकते हैं, वट एवर इज गुड फॉर यू।
सर एक बार डिसाइड करके बात करके सर आपको एक बार बोल देंगे सर, थोड़ा टाइम
ठीक है,
दीजिए बस।
श्योर, ठीक है, सोच के बता देना। ठीक है। और
राइट राइट सर।
तो आई थिंक सेकंड असाइनमेंट तुम लोग सबमिट कर देना। सो आई विल हैव 2 असाइनमेंट होगा और एक प्रेजेंटेशन के हिसाब से फिर मैं ग्रेडिंग भी कर दूंगा। ठीक है।
ठीक है सर,
ठीक है।
ओके सर।
ठीक है। ओके।
थैंक यू।
Okay, so we were looking at elliptic curves, and so today I'm going to give you some more background, and in fact the basic background I will cover, so that will be enough to understand elliptic curve Kruppler systems actually, so basically first lecture we gave you a couple of examples and we gave you the simplified version of these types equations. So today I'm going to give you a very brief idea of projective plane and actually how elliptic curves are connected there. So suppose K is a field. Field means where you can do all the 4 operations: addition, subtraction, multiplication, division. And K bar is a algebraically closed field. Do you know what is algebraically closed field? Any idea? Yes, anyone? Ajit, Praveen, Komal, Ashish. Any idea what is algebraically closed field? You see, uh, normally, if you look at what are the well-known examples of infinite fields, fields of rational numbers, fields of real numbers, and fields of complex numbers. So, out of these three fields, there is only one field which is algebraically closed, and other two fields are not. When we say algebraically closed field means you take any polynomial, it will split completely into factors over that field. So, any polynomial you take on reals or whatever, it will factor into complex, right? So, either complex and reals, both. So, essentially, field of complex numbers is algebraically closed field. Okay, so this is the idea of algebraically closed field. So you can take any algebraically closed field either in the case of infinite fields, this would be field of complex numbers, and in case of finite fields we actually define fq bar, so precisely define how to define algebraically closed field. So if k is a field, k bar is a algebraically closed field. Now we can define the projective plane. By the way, have you are you familiar with elliptic curves, or I'm just repeating the stuff, I mean, so the projective plane p square k over k is the set of equivalent classes of the relation this wiggled acting on the set k cube minus singleton 0. So the 0 point is not there, where x1 comma y1 comma z1 are 3 points equivalent to another point x2 comma y2 comma z2. So one point is equivalent to other point if and only if there exists u in k star, means non-zero elements, right? Such that x1 is multiple of x2, x2 is sorry y2 is multiple of y2, sorry y1 is multiple of y2, and z1 is multiple of z2. Okay, then we say that 2 points are same. So the projective plane is nothing but the set of equivalent classes. So basically what we are doing, for a given field k, we are forming k cube. So basically 3-dimensional space, deleting 0 point, and then between any 2 points, we say that 2 points are equivalent if and only if there exists a point u in k star such that this happens. Okay, k star is non-zero elements of k. Okay, so this is the basic idea. Okay, so we denote. Any question at this point? प्लीज आस्क. एक्चुअली अगर पूछोगे नहीं तो मेरे को समझ में नहीं आएगा कि तुमको कहाँ तक समझ में आ रहा है. एनी क्वेश्चन? यस अजीत, प्रवीण, एनी? या
सर अभी तक तो कुछ नहीं है, सब
ठीक है.
समझ आ
वेरी
रहा
गुड, वेरी गुड, वेरी गुड. नाउ व्हाट वी डू, so we denote the equivalent class containing at the point x, y, z by, just like that in case of integer modulo n, we denote 0 square 0 as 0, square 1 as 1, and so on, right? So we denote by x, y, z, equivalent class containing this point by this. Okay, now you have seen the V-star equation, a non-homogeneous form. I'm going to write down a homogeneous V-Strauss equation. So a V-Strauss equation homogeneous of degree 3 is given by y square z plus a1 xyz plus a3 yz square is equal to x cube plus a2 x square z plus a4 xz square plus z cube plus a6 z cube. So note that if we put z is equal to 1, we get the actual V-Strauss equation which is there. I would say non-homogeneous V-Strauss equation we will get. So homogeneous means you see the degree is 3 here. 2 plus 1, 3, 3, 3, 3. Each term has degree 3, right? So this is the homogeneous V-Strauss equation of degree 3. Okay. So sometimes people use homogeneous equation, sometimes people use non-homogeneous equation. Okay. So basically by doing some substitutions, we can convert a non-homogeneous equation into homogeneous equation by x is equal to x by z and y is equal to y by z. If we do that substitution, we will get this equation. And in this equation, if you put z is equal to 1, we will get back, the equation for uh, non-homogeneous equation. Okay. Now, so here these scalars ai's belongs to k bar actually. Okay, the algebraically closed field. Now the V-Strauss equation, I think I can go to the next slide. The V-Strauss equation is said to be smooth if or smooth or non-singular if for all projective points p is equal to x, y, z in the projective plane p square of k, satisfying the equation fx, y, z plus a1 x, y, z plus a3 y, z square minus x cube minus a2 x square z minus a4 x square a2 x square z minus a4 xz square, sorry, xz square minus a6 z cube barabar 0. So this is our equation. So we have, so for every projective point P in the plane satisfying this equation, if we have delta f over delta x at P, comma delta f over delta y at P, delta f over delta z at P is not equal to 0. Okay. If all the derivatives vanishes at P, then P is called a singular point. I think I already talked about these things in the last class, but now I am talking in terms of this homogeneous system called a singular point. Okay. Okay. So now What is elliptic curve? An elliptic curve, capital E, is the set of all solutions in the projective plane P square K bar of a non-singular Weierstrass equation. Okay. Now there is one special point here that I'm going to talk about, this that is known as point at infinity. So there is exactly one point in E with z coordinate 0. Okay, and that point is basically 0, 1, 0. This is the point. Z coordinate is 0. This is called as point at infinity, and it is denoted by O. Okay, so this is the point at infinity. So this presents on the electric curve, you know. So basically you can look at this point in this homogeneous system, you know, in the homogeneous Weierstrass equation. We can think about this point, you know. Sometimes when we look at the non-homogeneous system, it is difficult to visualize the point, so we need to look at this projective planes system. Okay, so there is one point in E with z coordinate 0, and this point is called as point at infinity. So as I told you earlier also, that if we do the substitutions, small z is equal to capital X by z, and small y is equal to capital Y by z in the non-homogeneous system. So then the homogeneous, yes, non-homogeneous will be converted into homogeneous system when we do this. Okay. So then so basically I can write down the equation y square plus a1 xy plus a3y is equal to x cube plus a2 x square plus a4x plus a6. So this is equation 2, I can call it, and this equation was equation 1. In the back here, this equation is equation 1. Equation 1 is a homogeneous system and equation 2 is a non-homogeneous system, and there is a relation. Okay, how we can go from one to the other. Now an elliptic curve E is the set of solutions to equation 2 in A bar cross K bar, the cross product of elliptically closed field, together with the extra point at infinity, which is O. Okay, so we write down this elliptic curve as is defined over K. That means E is defined over field K. In fact, there are theory of elliptic curves by Silverman. It's very nice book in 2 volumes, you know, but that discuss mainly on real and complex numbers. And for finite fields, there are many books available, especially Alfred Menges is one. They have a nice chapter there. Okay. E of K actually is the set of K rational points. Okay. Of E. Okay, so both coordinates lie in, so basically for these points, both coordinates lies in K together with the point O, the point at infinity. So EK is the set of all K rational points. K rational points means points that satisfy the elliptic curve, right? So both coordinates lies in K together with the extra point at infinity. Okay, so in fact, we can mention, I will not go into details, but I will at least mention the definition that two elliptic curves are isomorphic if they are isomorphic as projective varieties. So this is a term used in algebraic geometry. So right now I am not going, I think, into that business, because that itself is a lot of work. So, but that's a definition for two elliptic curves to be isomorphic. So in fact, I can give you an a relationship if and only if condition, and that will be enough for us. So this is a theorem. Two elliptic curves, E1 defined over K and E2 defined over K, given by Weierstrass equation E1 y square plus A1 xy plus A3y is equal to x cube plus A2 x square plus A4x plus A6, and second curve y square plus A1 bar xy plus A3 bar y is equal to x cube plus A2 bar x square plus A4 bar x plus A6 bar, right? So suppose there are two electric curves, E1 and E2, defined over the field K with the following Weierstrass equations. Then they are isomorphic. Isomorphic means there is a one-to-one and on-to map, which is, basically between the two, which preserves the algebraic structures, basically. Essentially, it will preserve the group also. Okay. Isomorphic over K. So we write it like that, that E1 is isomorphic to E2 if and only if there exists U, R, S, T in K, U is not equal to 0, such that the change of variable xy going into U square x plus R, U cube y plus U square sx. So U cube y plus U square sx plus t. Okay, this change of variable we are doing transforms E1 to into E2. Okay. So basically, these two elliptic curves are isomorphic given by these two Weierstrass equations. Okay, if and only if there exists U, R, S, and T elements in K, where of course U is not equal to 0, such that we can transform xy into U square x plus R and U cube y plus U square sx plus T. So once we do this change of variables, actually I can substitute these things in E1 and compare it with E2, right? So I can find out the values of the coefficients that are changing, So in fact, that is the next result that I can mention. So if E1 is isomorphic to E2 over K, This implies that U times A1 bar is equal to A1 plus 2S. When we do the comparison, we are getting these equations. A2 bar is equal to A2 minus S A1 plus 3R minus S square. U cube EA3 bar is equal to A3 plus RA1 plus 2T, and U4 A4 bar is equal to A4 minus SA3 plus 2R A2 minus T plus RS times A1 plus 3R square minus 2ST. And finally, U raised to power 6 A6 bar is equal to A6 plus RA4 plus R square A2 plus R cube minus T A3 minus T square minus RT A1. So these are the relations basically. So we can say that two electric currents are isomorphic to each other if and only if. So two electric currents E1 and E2 are isomorphic to each other if the relationship between the coefficients is given by this. Okay. So that means they will have same set of accurational points. That means the corresponding group will be also isomorphic. So that is an important thing. Now I think I am ready to describe the group laws to you. What are the group laws? So basically, set of all few rational points or any k rational points of the electric curve forms a group with respect to addition of points. So if I take a point P in a group and you add it certain number of times, I will get another point in the group itself, right? So that is a basic thing. In fact, in case of discrete log problem, as you know that when we implement this discrete log problem over this group of elliptic curves, we get elliptic curve proper system, because if we take a point capital P and add it m times, of course you will get Q, right? So P is known, Q is known, but solving for m is a difficult problem computationally, and that is the reason why we build elliptic curve proper system. Okay, so this is the basic idea behind it. So let me talk about this group and what is the law behind it. Okay, so the group law. So for every points P and Q in E, of course these laws which I am going to write, their rules are a little bit different in each group, depending upon whether the characteristic of the field is 2 or it is not equal to 2 or 3, right? In those cases the rules are a little bit different, but in terms of addition formulas are a little bit different, but nevertheless I can write down the these basic laws which are same. So for every points P and Q on the elliptic curve, point at infinity O plus P is equal to P and P plus O is equal to P. Okay. So either side you add point at infinity, you will get P itself. Second, minus O is same thing as O. One can prove these things. I am not proving right now. Just we want to mention it here. Third, if and some of these things can be proved using geometry actually. If P is equal to x1 comma y1, which is not equal to point at infinity, then minus P is equal to x1 comma minus y1 minus a1 x1 minus a3. If P is a point like this, which is not equal to point at infinity, then minus P is given by this. Okay, fine. Fourth point, if Q is equal to minus P, then P plus Q is equal to point at infinity, which seems to be obvious anyway. And fifth point, if P is not equal to point at infinity, Q is not equal to point at infinity, and Q is not equal to minus P, then let R be the third point of intersection and actually counting multiplicities of either the line PQ if P is not equal to Q. So of course, in that case, line is possible, or the tangent line to the curve at P if P is equal to Q with the curve. Then we also have P plus Q is equal to minus R. In other words, P plus Q plus R is equal to point at infinity. So these are the 5 laws of group. In fact, this group is abelian. One can show that this is a commutative group. Okay. Sorry. Okay. Next theorem that I would like to mention here. E plus is an abelian group with identity element O, right? If E is defined over A, then set of all k rational points ek is a subgroup of E. Okay, so this is the main result. Now I'm going to give you the formula for addition for the case 5, for case 5th, the case 5th here, I'm going to describe here. So if P is a point x1 comma y1 and Q is a point x2 comma y2 and P plus Q is a point x3 comma y3, let lambda is equal to y2 minus y1 divided by x2 minus x1 if P is not equal to Q, and it is 3x1 square plus 2a2x1 plus a4 minus a1 y1 divided by 2y1 plus a1 x1 plus a3 if P is equal to Q. Okay, so let lambda is this, and we can say that beta, suppose beta is this y1 minus lambda times x1, then x3 is equal to lambda square plus a1 lambda minus a2 minus x1 minus x2, and y3 is equal to minus lambda plus a1 times x3 minus beta minus a3. So the motivation for this, comes from the geometry. So right now I am skipping that technical details about how to arrive at these things using geometry. So one way could be we simplify the equations and consider the equation when characteristic is not equal to 2 or 3, and we try to draw the pictures and see what happens to the elliptic curves points when we add. Okay, so there are different ways, and finally, people have concluded that these are the points. Now, one important concept, two important concepts. One is discriminant, and the second is J invariant of elliptic curves. I'm going to define them. So if E is a elliptic curve given by non-homogeneous Weierstrass equation, okay, then you define certain quantities as D2 is equal to A1 square plus 4A2, D4 is equal to 2A4 plus A1A3, D6 is equal to A3 square plus 4A6, D8 is equal to A1 square A6 plus 4A2 A6 minus A1 A3 A4 plus A2 A3 cube minus A4 square. C4 is equal to D2 square minus 24 D4. Delta is equal to minus D2 square D8 minus 8 D4 cube minus 27 D6 square plus 9 D2 D4 D6, and J of E is D4 cube divided by delta. Okay, so these quantities we define. So here this quantity delta is known as discriminant. Discriminant of the elliptic curve E, and this is known as J invariant. So J invariant of elliptic curve, So note that this is defined if, of course, discriminant is not equal to 0. Otherwise, this will not be well defined, right? So these two quantities are very, very important. So now there are some characterizations using discriminant and J invariant. Some results I'm going to mention. The first result is, so E is given by the Weierstrass equation. So then E is an elliptic curve. This is a direct calculation. We can use this result. That is, Weierstrass equation is non-singular if and only if discriminant is not equal to 0. Okay, the first result, an important result. Next, I think I can mention next result, which is with respect to J invariant. If two elliptic curves E1 over K and E2 over K are isomorphic, over K, then their J invariants will be the same. J invariant of E1 is same thing as J invariant of E2. The converse is also true. Okay, so the converse is also true if K is an algebraically closed field. In that case, converse is true. For example, if K is a field of complex numbers. Okay. And one last result here. If two elliptic curves are isomorphic, then they are also isomorphic as abelian group. Converse is not true. Anyway, so this is the main result. Now I think I can give certain addition formulas. The one which we described here earlier are like this one is a very general one. Okay, but now I can describe some simple formulas because when we put some conditions on the field. Basically, first I'm going to look at curves over K, where characteristic of K is not equal to 2 and 3. Okay, so if characteristic of K is not equal to 2 and 3, we can assume that, I think you remember from the last class that we have a simpler version of the V-star equation. We can assume that E over K has the form E y square is equal to x cube plus ax plus b. Okay, where a and b are elements in K. In that case, the discriminant is given as minus 16 4a cube plus 27 b square. This is a simplification, and J invariant of E will be minus 1728 times 49, sorry, 4a cube divided by delta. So for this curve, when the characteristic is not equal to 2 or 3, we can have the addition formula, So if P is equal to x1, y1 in E, then minus P x1 comma minus y1. Okay, it's kind of reflection, and if Q is equal to x2, y2 in E, and Q is not equal to minus P, then P plus Q can be written as x3 comma y3, where x3 is lambda square minus x1 minus x2, y3 is lambda times x1 minus x3 minus y1, where in both the cases lambda is equal to y2 minus y1 divided by x2 minus x1 if P is not equal to Q, and is equal to 3x1 square plus a divided by 2y1 if P is equal to Q. So these formulas are easy to implement actually, of course, in Perry GP and so on, addition formulas. You choose the field and you can actually add the formulas, you can add the points in the electric curve. Anyway, next is the characteristic 2, when the field has characteristic 2, which is a very special case, So let me talk about that. Curves over K with characteristic of K is equal to 2. Okay, so K is a field of characteristic 2 E over K. So electric curve over K given by V star's equation. In this case, you remember that E is of the form y square plus a1 bar xy plus a3 bar y is equal to x cube plus a2 bar x square plus a4 bar x1 plus a6 bar. Okay, so J invariant turns out to be a1 bar raised to power 12 divided by delta. Now, there are two cases possible here. If J invariant is 0, that means a1 bar is not equal to 0. Sorry, a1 bar is equal to 0. Oh, I am sorry. If the J increment is not equal to 0, so a1 bar is not equal to 0. Okay. So the change of variables that we can do, xy going to a1 is bar square x plus a3 bar slash a1 bar comma a1 cube y plus a1 bar square a4 bar plus a3 bar square divided by a1 bar cube. By doing this change of variables, electric curve will become E1 y square plus xy is equal to x cube plus a2 x square plus a6. Okay. So for this E1, delta A turns out to be a6 and J invariant turns out to be 1 over a6. Okay. So in the case when J invariant is not equal to 0, in this case characteristic is 2. So this is a simplification. Okay. And the second case, if J invariant is 0, if J invariant of E is 0, that means a1 bar is equal to 0. Then we do the change of variables as xy goes to x plus a2 bar comma y. Okay. So basically, yes, this is closed. Y, and in that case, basically we get electric curve E2 as y square plus a3y is equal to x cube plus a4x plus a6. For this E2, discriminant turns out to be a3 raised to power 4 and J invariant of E2 turns out to be 0. Okay, so that is the thing. Now I think in both the cases we have the addition formula, so I can describe the addition formula for you. The first one is when J invariant is not equal to 0, P is x1 y1 belongs to E1, then minus P is x1 comma y1 plus x1 if Q is equal to x2 comma y2 in E1 and Q is not equal to minus P, then P plus Q is equal to x3 comma y3, where we can actually find out the values of x3, and so x3 turns out to be y1 plus y2 divided by x1 plus x2 whole square plus y1 plus y2 divided by x1 plus x2 plus x1 plus x2 plus a2 if p is not equal to q and is equal to x1 square plus a6 divided by x1 square. Okay, if p is equal to q. x3 is this, and we have y3 is equal to, it's a bit lengthy formula, but y1 plus y2 divided by x1 plus x2 times x1 plus times x1 plus x3 plus x3 plus y1 if p is not equal to q and is equal to x1 square plus x1 plus y1 divided by x1 times x3 plus x3 if p is equal to q. Okay, so these are the addition formula when the J invariant is non-zero, and when J invariant is equal to 0, addition formula is a little bit different. In the case of characteristic 2, so if p is equal to x1 y1 in E2, then minus p is equal to x1 y1 plus a3 if q is equal to x2 comma y2 in E2 and q is not equal to minus p, then then p plus q is equal to x3 comma y3, where x3 is y1 plus y2 divided by x1 plus x2 whole square plus x1 plus x2 if p is not equal to q and is equal to x1 raised to power 4 plus a4 square divided by a3 square if p is equal to q. This is x3, and similarly an expression for y3 is given. The addition y3 is equal to y1 plus y2 divided by x1 plus x2 times x1 plus x3 plus y1 plus a3 when p is not equal to q, and x1 square plus a4 divided by a3 x1 plus x3 plus y1 plus a3 if p is equal to q. Okay, so I think these are the basic addition formula. Now I am going to come to the very interesting. So these are the general cases, all these are the general cases. Now we come to a very interesting result. I will give you the structure of the group and the number of points in the group. So now we focus on finite field Q. Q is a prime power. Okay. So E is an elliptic curve over FQ. Fine. So number of EFQ stands for number of points.
सर
Yes.
एक्सक्यूज मी
Yes, बोलो.
सर सॉरी टू इंटरप्ट यू सर, एक्चुअली सर 3 बजे क्लास है हमारा इंग्लिश का.
अच्छा ठीक है, तो वी कैन डू इट इन द नेक्स्ट टाइम, नो प्रॉब्लम. ठीक है, तो
Thank you,
या
sir.
दिस ठीक है, विल मीट नेक्स्ट टाइम.